Section 8.1, the Pythagorean Theorem and its converse. Theorem 8.1 is the Pythagorean Theorem, and it states in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Here we have a right triangle in our diagram, vertice A, B, and the right angle at vertice C. And in triangles, we label the lengths of the sides opposite the vertex in a lowercase letter. For example, here we have side CB. It is labeled lowercase a because it is opposite vertex A. Here we have hypotenuse AB. It is labeled lowercase c because it is opposite the vertice C. And again, we have side AC, which is opposite vertice B, and it is lowercase b. And by formula, the Pythagorean theorem is a squared plus b squared equals c squared. In other words, the sum of the square of the legs is equal to the square of the hypotenuse. Here we want to find the value of x in each diagram. Leave the answer in simplest form. What we want to do is use the Pythagorean theorem. As stated before, it is a squared plus b squared equals c squared. We don't care what leg is labeled which. We do care what the hypotenuse is labeled. We have to just make sure that the legs go in for A and B, and the hypotenuse goes in for C. Here, we have legs 4 and 8, so we substitute 4 squared plus 8 squared equals the hypotenuse, which is x squared. Then we just solve the equation for x. Here, 4 squared is 16, 8 squared is 64, equals x squared. 16 and 64 is going to give us 80, equals x squared. Then we take the square root of both sides. And when I do that, I'm going to get x equal to the square root. Then I must break 80 into two factors. One is a perfect square and one would not be a perfect square. Here, I'm going to break this into 16 times 5. The square root of 16 is 4, and 5 stays in the radical. On our next example, again, we're going to use the Pythagorean theorem. A squared plus b squared equals c squared. Our leg, 5, and x, we substitute in for a and b. 5 is 5 squared. For b, I'm going to put in x squared. It's a leg. And for c is 16, our hypotenuse. We simplify. 5 squared is 25 plus x squared equals 16 squared, which is 256. Subtract 25 on both sides, I get x squared is equal to 231. I notice that this is not going to work out evenly, so I'm going to substitute that into a calculator. And when I do, x is going to equal approximately 15.198 or 15.2. In my next example, I have another right triangle. Therefore, I want to use the Pythagorean theorem to solve for x, which is my hypotenuse. Just make sure that A and B are my legs. Here, one leg is 12, and the other leg is 16. And then I set that equal to my hypotenuse. In this case, it is x. Simplify. 12 squared is 144. 16 squared is 256 equals x squared. Combining these terms, I'm going to get 400 equals x squared. Take the square root of both sides. X is going to equal 20. On my next example, I see that I'm given a right angle on one of my vertices, and I know that I have 4 congruent sides, therefore I have a square. This tells me that these two segments are congruent. Therefore, I can use the Pythagorean theorem again in this triangle of my square. Therefore, a squared plus b squared equals c squared. Making sure the legs go in for a and b, which would be 9 and 9. And x for my hypotenuse. It gives me 81 plus 81 equals x squared. And that gives me, when I combine these two terms, 162 equals x squared. Take the square root of both sides. Therefore, x is equal to the square root of, breaking 162 into two factors, one being a perfect square, which would be 81 times 2. The square root of 81 is 9, and 2 is left in the radical, 9 square roots of 2. On my next diagram, again, I'm given a square, but here, my legs are the unknown value. Therefore, this is x, and since this is congruent, this is x. And my hypotenuse is 12, but I can still use the Pythagorean theorem. A squared plus b squared equals c squared. But in place of a and b, which are my legs, are x squared plus x squared equals, for c, 12 squared. Combine like terms, I'm going to get 2x squared equals 144. Divide by 2 on both sides. X squared is equal to 72. Take the square root of both sides. I'm going to get x equals the square root of 72, but that can break up into two factors, one being a perfect square, which is 36 times 2. The square root of 36 is 6. 2 stays in the radical. Therefore, each leg is 6 square roots of 2. On this example, I'm given an isosceles triangle, and I have an altitude from the vertex angle. Since this is an isosceles triangle, I can get these two angles congruent. I know that these two angles are already congruent because they are both right angles, and I know that this segment is reflexive. Therefore, the triangles are congruent by angle, angle, side. Since that's true, I know that this altitude bisects this side. Therefore, this segment must be 4. Now that I know that this leg is 4, this leg is x, that is the hypotenuse of this right triangle, I can use the Pythagorean theorem to solve for that leg. A squared plus b squared equals c squared. Substituting in my legs and hypotenuse, A, I'm going to let be 4 squared. B is going to be x squared. And c is the hypotenuse, which is 16 squared. Simplifying, I'm going to get 16 plus x squared equals 256. Subtract 16 on both sides, I get x squared equal to 240. Then take the square root of both sides. Break this into two factors, one being a perfect square, and those factors are 16 times 15. Square root of 16 is 4, and 15 stays in the radical. Therefore, the leg is 4 square roots of 15. Our next definition is a Pythagorean triple. That is a set of non-zero numbers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared, which is the Pythagorean theorem. Our common Pythagorean triples are listed here: 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. But what does that actually mean to you? That means if I take the two legs of this set of numbers, remember the legs are smaller than a hypotenuse, so here 3 and 4 are the legs, and substitute those legs and the hypotenuse into this formula. That would be 3 squared, which is 9, 4 squared, which is 16, equals the hypotenuse, which is 5 squared, which is 25. And when I simplify the left side, I get 25 equals 25. If I would do that in each one of these cases, I would get the Pythagorean theorem, the sum of the square of the legs equals the square of the hypotenuse, to work out exactly the same for each one. They would form a right triangle. But here I know that I have triples. In this instance, what I can do is multiply each set of these numbers by a common multiple, and that set of numbers is also a Pythagorean triple. For example, if I would multiply each of these numbers by 2, that would be 2 times 3, which is 6, 2 times 4, which is 8, and 2 times 5, which is 10. If I substituted that into the Pythagorean theorem, I would end up with a right triangle. For example, that would be 36 plus 64 equals 10 squared, which is 100. 36 plus 64, 100 equals 100. Therefore, I know if I would have 6, 8, 10, that is an original 3, 4, 5 triangle, and that is a right triangle. Another way to look at this is I can multiply this by 3 and get 9, 12, 15. Multiply it by 4, 12, 16, 20. This set of numbers are multiples of a 3, 4, 5. Therefore, these are all right triangles. I can do that for each set of numbers. A 5, 12, 13, substituted into the Pythagorean theorem, is a right triangle. The left side equals the right side. I also know if I multiply this by multiples, each of those sets of multiples is a right triangle. For example, multiplying by 2, 10, 24, 26. Or multiplying by 3, 15, 36, 39. These sets of multiples of 5, 12, 13 are all right triangles. And that is similar for 8, 15, 17, 7, 24, and 25. So try to remember, when you take a look at the legs and the hypotenuse of a right triangle, that if it forms one of these sets of numbers or sets of multiples of those numbers, that you don't have to worry about the Pythagorean theorem. You already know that it's going to be a right triangle. Theorem 8.2, the converse of the Pythagorean theorem. Remember, if we have an if-then statement, if P then Q, the converse is if Q then P. So that's what we're going to do from the Pythagorean theorem, is use the converse, which is if Q then P. If the square of the length of one of the sides of a triangle is equal to the sum of the squares of the lengths of the other two sides of the triangle, then the triangle is a right triangle. In other words, just as I performed on the last page, if I know that a squared plus b squared equals c squared, then I know that I have a right triangle. Therefore, to verify that I have a right triangle, I take the two smallest segments of the figure given and see if that equals the longest segment. If it does, then I know that that longest segment is the hypotenuse, these two segments are the legs, and I have a right triangle. We can take that a little bit further, that if they're not equal, then theorem 8.3 states if the square of the length of the longest side of a triangle is greater than the sum of the squares of the lengths of the other two sides, the triangle is obtuse. In other words, performing the Pythagorean theorem, if I find out the longest segment is greater than the sum of those two other segments, then I know I have an obtuse triangle. Theorem 8.4 states if the square of the length of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, the triangle is acute. Therefore, if the longest side is less than the sum of the other two sides, then I have an acute triangle. If it's greater, it's obtuse. If it's less than, it's acute. If it's equal to, it's a right triangle. On this example, the lengths of the sides of a triangle are given. Classify each triangle as acute, right, or obtuse. So we're going to use c squared equals a squared plus b squared. If c squared is equal to the sum of the square of the other two legs, then I know that it is a right triangle. If c squared is greater, then it's going to be obtuse. If it's less than, then it's going to be acute. Therefore, I'm going to use c squared. I'm going to determine that by equal, greater than, or less than a squared plus b squared. The longest segment is c, therefore 1 squared. A squared is going to be 0.5 squared. And b squared is going to be 0.7 squared. Simplify, 1. That gives me 0.25 plus 0.49. Therefore, when I simplify the right side, I get 1. 0.25 plus 0.49 is 0.74. Therefore, 1 is greater than 0.74. Therefore, this triangle would be obtuse. Next, I have 15, 20, and 25. If I do the same thing as before, I'm going to have c squared compared to a squared plus b squared. My largest segment is 25 squared, which is going to be 625, compared to 15 squared is 225, plus 20 squared, which is 400. Combining the right side, I get 625 equals 625. Therefore, these are equal. And since that has c squared equal to the sum of the square of the legs, this is a right triangle. I also could have noticed that 15, 20, and 25 are all divisible by 5. Therefore, if I would take 15 divided by 5, I get 3. 20 divided by 5 is 4. And 25 divided by 5 is 5. Therefore, I would realize that this is a Pythagorean triple and not have to go through the work of testing the previous theorems. I would know that this is a right triangle because it is a Pythagorean triple. And on my last example, I'm going to again use c squared and compare that to a squared plus b squared. Here my longest segment is 4. Therefore, that's going to give me 16 compared to a squared, which is going to be the square root of 2 squared, which is the square root of 2 times the square root of 2, which is the square root of 4. Square root of 4 is 2, plus 3 squared, which is 9. I know I have 16, and 2 plus 9 is 11, and 16 is greater than 11. Therefore, I know that this must be obtuse.